Alright, we're going to be doing problem number 49 out of chapter 26 of Physics for Scientists and Engineers, second edition by Knight. Alright, so let's see, problem number 49. I already took the liberty of drawing out the diagram, so I don't have to waste time with that. So you've got this negatively charged particle in the middle at -3 nanocoulombs. And you got Q1 over here, Q2 over here, and they're all spaced 10 centimeters apart. Alright, and so the question states that Q2 there is in static equilibrium. What is Q1? Alright, so let's talk about what that's asking for. Required. Okay, so it's saying Q2 is in static equilibrium. Alright, Q2. And what is charge on Q1? Alright, so the theory goes that it actually, we're going to find out it won't really matter what the charge on Q2 is, and that it's a function of this charge and this distance versus this charge and the total distance of both of these, where this will remain in equilibrium for any charge of Q2. Alright, so let's make this easier to identify some things. We'll put a charge or a force that way and a force that way. Let's call this particle A, this particle B, and this particle C. So that would, let's assume that it is drawn towards the particle here. These be anchored, and so we're going to call this force AB, and this one over here force AC. So the particle here is drawing this, is pulling Q2 towards it, whereas Q1 is pushing particle Q2 or particle A away, force AC over here. In order for it to be in static equilibrium, solution, okay, that means that FAB plus FAC equals 0. That would be F net equals 0. Alright, so let's start coming up with some formulas for what FAB and FAC are. I'm going to eliminate, I'm not going to use R hat for this. This is all one-dimensional, so we could just stick with magnitudes and there won't be any trigonometry. So let's see, FAB equals, let's use Coulomb's law, so 9 times 10 to the 9th Newton meters squared per Coulomb squared times, we got Q2 in there, that's a charge, Q2 times this one here, which is negative 3.0 times 10 to the negative 9th coulombs, and that is all over this distance, which is 0.1 meters squared. I suppose I should keep our significant figures correct here. Alright, so let's do the other one. FAC is equal to, once again we got that K constant in there, times 10 to the 9th Newton meters squared over Coulomb squared. We got Q2 because we're going between Q2 and Q1. Alright, so Q2 and Q1, and then that is all divided by the distance between those, which is 10 plus 10, 20. Okay, so 0.20 meters squared. Okay, so let's see, FAB plus FAC equals 0. That means that we could say FAB is equal to negative FAC. And in doing so, we're going to find that a lot of these terms can just be divided out. The K constant will be divided out, as well as Q2 goes away. And what you end up with is negative 3, there's a negative sign here, so FAB, okay, negative 3.0 times 10 to the negative 9 coulombs over 0.10 meters squared equals Q1 over 0.20 meters squared. A little more visible. Alright, so you do some cross multiplication and then you solve for Q1, and it turns out that Q1, oh, there's a negative here because, right, we have negative FAC, this is FAC side, so let's throw a negative in there. And then it turns out actually this negative and this negative cancel out. Let's see, what I ended up with here is 1.2 times 10 to the negative 8th coulombs, which is the same as 12 nanocoulombs. Alright, so let's see, so this is a positive number. I kept everything with respect to positive and negative, so Q1 is a positive charge and it equals 12 nanocoulombs. Yeah, that's the solution to that one right there. I hope that answers any questions anyone has.